Welcome to our Quantum Deep Dive. So today, we're exploring a pretty groundbreaking concept from an essay by Jorg O.A. Schneepat. It's called Quantum Rejection Sampling.
Yeah, and it's all about a revolutionary new way to find that one perfect data point. You know, the pure signal that's buried in a vast sea of digital noise.
So Schneepat kicks things off by reminding us that our world, everything from financial markets to drug discovery, it all runs on finding meaningful patterns, and that all begins with getting the right samples.
But here's the real question. What if our tools for finding those samples are just fundamentally broken when problems get really, really big?
Well, that's the quest we're on today.
So we'll start by understanding the classical way of doing things and, why it struggles so much.
And then we'll dive straight into the quantum toolkit that offers the solution. We'll define quantum rejection sampling itself, and finally, explore what it all means for the future.
Okay, let's dive into this. To really understand the quantum leap we're talking about, we first need to get a handle on the classical method, rejection sampling. The best way to think of it is as a very meticulous quality control inspector on an assembly line.
It's actually a pretty clever and universal tool. You've got this complex pattern you want to sample from, but it's just too hard to do it directly. So what you do is you use a simpler, broader pattern to generate candidates, and then you decide which ones you're going to keep.
The process itself is really straightforward. You propose a candidate, run a probability test, and then you either accept it or you reject it. The key is that this works perfectly, but, and this is a big but, it can be incredibly wasteful.
And this chart, wow, it just brilliantly illustrates the problem. The inspector has to pick up and examine thousands, maybe millions of items just to find a handful of good ones. It works, for sure, but the cost in time and computation is just enormous.
Exactly. That inefficiency you were just talking about isn't just some small annoyance. For the kinds of problems we're facing today, it becomes a complete roadblock.
Yeah, because modern data isn't a simple assembly line. It has thousands or even millions of dimensions. Think about AI models or complex molecular simulations. So, what happens to our inspector then? In a simple problem, maybe you find one good sample out of 10. That's manageable. But as the complexity grows, that rate just plummets. Now it's 1 in 1,000. And in these crazy high-dimensional spaces, it can become 1 in 1,000,000 or 1,000,000,000. The number of rejected samples just explodes exponentially. Our inspector is completely and totally overwhelmed. And this phenomenon, well, it has a name. It's known as the curse of dimensionality. And at this point, the classical brute force approach simply stops being a viable option. We've hit a wall. So, the big question is, how do we get over this wall? Well, the answer lies in changing the rules of the game entirely by using the principles of quantum mechanics. Okay, now what's really interesting here is the fundamental difference. A classical bit, it's basically a light switch, on or off. A qubit, though, thanks to something called superposition, can be both on and off at the exact same time, representing a huge number of possibilities all at once.
And we can manipulate all of those possibilities using a tool called amplitude amplification. So instead of checking every single item one by one, we can look at all of them at once and use quantum interference to make the good ones, well, stand out. It's like they start to glow brighter.
So now we have the tools. Let's see how they totally transform our sampling problem with something called quantum rejection sampling, or QRS for short.
QRS completely flips the script. It's not about rejection anymore. It's about amplification. Our quantum inspector doesn't need to search through a pile of junk. The perfect items now basically call out to be picked. And this chart brilliantly illustrates the payoff. The number of steps, all that computational effort, gets quadratically reduced. So something that took 1,000,000 classical attempts might now take only 1,000 quantum steps. This is a complete game changer for problems with really low acceptance rates. The process is, okay, a bit more complex, but the outcome is nothing short of revolutionary. It replaces that inefficient cycle of propose, test, reject with a coherent quantum process of prepare, amplify, measure. So we have this incredibly powerful new tool. The question is, what new worlds can it unlock? Oh, the impact is absolutely enormous. We're talking everything from designing new drugs and materials in quantum chemistry to building way more powerful and efficient artificial intelligence. QRS provides a fundamental speed-up for all the probabilistic tasks that underpin these massive fields.
We've really only scratched the surface of this fascinating topic.
And our explanation today is based on the really comprehensive essay on QRS by Jörg Owe Schneff.
So if you want to explore this and other quantum technologies further, we highly recommend visiting his website at schneppatz.de.
So, we'll leave you with a final thought. QRS shows us that we can use quantum mechanics to basically manipulate probability itself. So the crucial point is, what's the next impossible barrier we can break?
Thank you for joining our deep dive, and goodbye.
Schneppat.de is a private project by Jörg Owe Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.